So, what have we done in chapter 7? We have looked at the idea of comparing two dependent groups, where I'm looking at a group before a treatment of some kind, and then after a treatment, and I want to see if there's a difference that's significant enough to tell me the effects of the treatment. Now we want to look at two independent groups, and the first example should illustrate the difference between what we've done before and what we're going to do, what we're trying to consider now, where I'm looking at two groups measuring their task performance in a quiet environment and a noisy environment. So these are different people. I'm not taking the same group and putting them into two different situations. I have different people and different number of people potentially. Some of them were rated in the quiet environment and other people were rated in the noisy environment. So the groups are independent. I can't take differences because I don't have the same people. Who do I pair up? It doesn't make sense to pair people up. I don't even have the same number of people. So I'm simply trying to look at the average of the first group and the average of the second group as representative of those population of all people in the quiet condition. This sample is hopefully representative of how people would do in this situation. And this sample is hopefully representative of how people would score in the noisy environment. And I'm trying to see how those two means compare. So it's not the same situation as before, but I'm still trying to compare two means, now two independent means. Everyone happy that the situation is different? Different. That's all we want to know. It's not the same as before. I can't take the differences in the same way. It's not the same situation. Similar, not exactly the same. So, the hypothesis question or the hypothesis test issue is still, is there a significant enough difference between the two means? How do the means compare between these two populations based on the samples that I have? So let's go to the next, the hypothesis test procedure. It just started. We're going to jump around a little bit. The first part should be fairly familiar in how we phrase them. So I have two populations. One population tested under quiet conditions, one population tested under noisy conditions, and my research hypothesis is what I hope would be supported by the evidence, that under quiet conditions they score better. In other words, population 1's mean is greater than the mean of population 2. So the mean in quiet conditions is greater than the mean in noisy conditions. And then the null hypothesis is that it's not. That it's not. That people in the quiet conditions don't perform better. Everyone happy with the setup? Setup should be familiar. Right. The problem is estimating the variance. Isn't that always the problem? The variance, tricky. So what we can assume, or have to assume, is that both populations have the same variance. That people have the same variability in terms of how they perform regardless of the situation. On average, they perform better or worse in the different situations, potentially. That's what we're trying to investigate. But I'll assume that the variance is the same from each of the populations. So I can estimate the variance from each sample and then combine those two estimations to give me a population variance estimation. Let's just pause this for a second, and I'm going to ask a seemingly completely unrelated question. Let's go off topic. If I have two midterm scores, and let's suppose in a simple course I have my whole grade is made up out of two midterms, that's two tests. Test 1 contributes, let's say, 60% of my final grade. And 1. Test 2 contributes 40% of my final grade. How do I determine, now when I score test 1, I score, let's say 70%. And in test 2, I score 75%. What's my average percentage for the course? It's not just this plus this divided by 2. Because test 1 carries more weight when I calculate my overall grade. So it's what I call a weighted average. Weighted average. Sorry, my pen is really not working with me here. Let me down, pen. Weighted average. Where there are different ways to say it, where I take test 1 percentage or score and I weight it according to the 60%. So you can go 60 out of 100 if you want to. It's a fraction of the 100%. And I take my test 2 score and weight it a little bit less according to the 40%. And then I would get my overall percentage, which would be, I want to calculate this, 72? 72%. Now, there is a difference between this and 70 plus 75 over 2. Not very much, because it's only a 60-40 split. If this was if this was closer to 100 and this was contributing less, then the actual correct average would be further away from just the simple average of those two. So I call this a weighted average, because they contribute in different ways. Does that make sense? Now we're going to do the same thing when I estimate the variance, in that I have samples of different sizes. If I calculate the sample variance from each one, and I want to pool them together to give me a population variance estimate, the bigger sample should have a little more say in what the variance is. If I have a smaller sample, it shouldn't have as much say. So I'm going to calculate what we call the pooled variance as an estimation of my population variance by calculating a weighted average according to the sample sizes. Okay. I'm trying to get the concept first before worrying about the detail of the calculation. Okay, so I'm going to scroll up, but I don't want to look too far. What is this? 2. So I don't want to show too much, but So here we have the two samples. Now I'm trying to estimate the variance. So I'll calculate the variance for each one. Looking at the average, of course, the sample mean. 21 in this case, add them up, divide by 5. Add this one up, divide by 4 to get a mean of 17. Then I look at the deviations, squared deviations. Sum of the squares is a 10 in this case. And I'm estimating the variance for this this group. So I'll divide it by 5 minus 1, and I get a variance of 2.5. So the mean is 21, the variance is 2.5, degrees of freedom is 1 less than the sample size. Same for the second sample, mean is 17, variance is, I'll call variance 2, is 4.67, degrees of freedom is 3. So now I'm going to calculate the pooled variance. I'm going to have to scroll up a little bit, but don't look past this. Don't look at this. Don't look at it. I can cover it up, but you can still see it. This is as far as I'm going to go right now. Just building it up slowly. So the total degrees of freedom, I'm just going to add up the two separate degrees of freedom. That's the number that works. Now I'm going to calculate a weighted average and use that as the estimation for my population variance. Because I have a 5 sample and a 4 sample. So I'm going to weight it according to the degrees of freedom, which is the same or similar to the sample size. The bigger sample will have a higher degree of freedom, so it should carry more weight. So this one has a slightly higher degree of freedom, so it'll have a weight of 4 out of 7. And this one will have a weight of 3 out of 7. So the estimation for the population variance, the first sample will have a little bigger say in what the estimation is. Bigger samples, and they're probably better representations of the variance of the population. They should have a little more say. So I'll combine the two separate sample variances into what I call a pooled variance, and that'll be my estimation for the population. So the calculation here, combine the two, and I get a variance for my population of 3.43. Everyone okay with the weighted average idea? Everything we're doing from now on gets a little more complicated, a little more complicated. But hopefully before it gets too much, we're done. That's sort of the goal. It's inevitably going to be more complicated. It's statistics.
Is the final one you opened up to?
Is it cumulative?
It's as non-cumulative as I can make it. But there's always going to be overlap. It's unavoidable. And whatever the midterm is, the final is as well. Unless people don't want it. I'm open to suggestion. I don't really mind. Whatever makes this more pleasant experience, I'll go for. Damage control, yes.
So, whichever one is more weighty.
Weighty, sure. Whichever one is the bigger sample has more say in what the variance should actually be.
So that is where you, I can't really see this, but that's where you do.
Should I zoom in?
Yes, please.
Now look at this.
So where is that represented? The fact that it's more.
Here. So the degree of freedom corresponds to the sample size. Right?
Yeah.
If the sample is bigger, the degree of freedom will be bigger. So in this case, they're close, but the first one's a little bigger than the second one.
Yeah.
So the first one has a 4 out of 7 say, and the next one has a 3 out of 7 say, making up 7 sevenths.
Oh, okay.
So instead of our percentages, it's now out of 7.
Yeah.
Because the total degree of freedom is 7. 4 of those 7s, the first sample has sort of a say, a little more than half the say,
Yeah.
because it comes from the bigger sample. Now this is very slight, so it's very close to half and half, but if the samples were more unbalanced, then it would be even worse.
Okay.
Because the bigger sample is hopefully more representative, so we'll have a sample variance that's closer to the population. So I want that to have more say in trying to aim for the actual population variance.
Yeah, okay. Thank
Those things in brackets, that's not like
This
four, yeah, like that, and then later, that's not like 4/7 times 2.5.
It's times, yes.
That is multiplying.
Yes.
Where is the 2.5 coming from?
This is the sample variance from sample 1. Sum of the squares divided by 5 minus 1. 2.5. This is the sample variance from sample 2. Sample 2. But it has a smaller say because it's a smaller sample. Variance is a tricky guy.
What are we trying to accomplish right now?
We're trying it's a good question. Fair question. In life or in the course? I don't think I can answer. I can answer this one. We're trying to get as accurate as possible an estimation of the population variance. So both samples are giving me some information. I want to incorporate them both, but in a way that I point as accurately as possible to the actual population variance. So the bigger sample, I think, is going to point a little better. But I don't want to I don't want to ignore the second sample completely. I want it to have a say, just not as much. Because maybe it has something to say, so I want to mix them. And that's really my best chance. I don't know for sure, right? I can be way off, but it's my best estimation based on the sample. Educated guess. Educated guess. Any other questions? Questions are good? Okay, so don't look too far ahead. So that the pooled variance will be the estimate for my population variance. So now I need to again look at the two means and what are their distributions, each of the two populations, right? Each of the two populations, they're different. The people working in quiet conditions, the people working in noisy conditions, different. And this is a sample of more than one, so I'm going to need to compare this sample mean to the distribution of all possible means in the quiet condition. And I'm going to have to look at this sample, which is more than one. So I'm going to look at how this sample mean of 17 sits in the distribution of all sample means for 4 people working in noisy conditions. So I have 2 of them. Let's visualize. Can I visualize this? I have 2 populations. Quiet condition, people, individuals, task performance, and noisy condition. But because I have a sample that's bigger than 1, I need to look at the distribution of means, just as we've done before, more than once now. So I convert each one to its distribution of means. That's the next step. Because I have a sample that's more than 1, I need to look at where that sample average sits among all possible sample averages of 5 people that I can get. Where the sample average for my sample of 4 people, where that sits among all possible average ratings that I could get from 4 people in a noisy environment. trying to say this in different ways until you get it. So let's go up. That was 8.3. So actually, let me go just back to the calculation here for a second. Yeah. So now the next step is going to be the variance for my population's distribution of means. I have two of them. Bring them both down. Sample 1, was it the quiet one? Quiet is sample 1, okay. Just want to refer to these things correctly. Sample 1, the variance for the distribution of means for all groups of 5 people working in quiet environments. I take the population variance, which is the same for both, and just like before, I divide it by the sample size. Same for the second one, because now I'm going from the population to the distribution of means. Same as before. Whether you write the variance is, how should I write it? Whether you write it like, whether you write this over n in general, squares, right? Or whether you write the standard deviation as the individual population standard deviation over root n, it's the same thing. That's how we've been calculating. That's how we've been going from the population mean, from the population distribution to the distribution of means. And I have to do that because I'm working with a sample. I need to see a sample of more than one individual. I need to see where that sample average sits among all possible sample averages that I could possibly get. That's what we've been doing for 2 days now.
I thought we usually take the square root of the whole thing, not just the n.
Well, you are though.
No, I did that, yeah.
Yeah.
Different ways to do this.
Oh, I see.
Square. And then because this guy cancels the square,
Right,
there's
yeah.
different ways of writing the
Oh,
sentence.
okay. And
So
then,
my personal choice is this,
Right.
but on the slides they seem to go this route.
yeah.
doesn't
Oh,
it?
okay. And then also, because we took the, we're trying to figure out the standard deviation of the population, so we took the variance of the population. But why would we only use the population of one of them and not the population of the whole thing?
Where this one?
Yeah, the n.
Because the sample sizes are different. And sample size affects the distribution of means in terms of how thin or thick it is. It affects its variance. So now in this case you could intuitively argue that they're so similar. What's the issue? 5 versus 4, yes. But if I have like a sample of 10 versus a sample of 3, then if I look at how the sample, if I have a large sample, let's say N1 is 10 or bigger, and a small sample, N2 is 3. Why do I keep using blue? I have others here. Then if I look at how this specific sample mean that I got, how that sits among all possible sample means that I could get from a sample of 10 is going to be different in terms of the variability than if I looked at a sample of just 3. This is going to have a lot of variability. This one not as much. So when I'm comparing how the sample sits within its distribution, I have to look at them separately initially. This one might have a fairly thin distribution of means because, okay, let's exaggerate and make it 100. It might be fairly representative, so I don't see a lot of variety between different samples of 100. Whereas if I take a sample of 10, it's going to have a lot of variety because so many different things can happen. Sorry, example 3. So many different things can happen if I just look at 3 people at a time. Many different things. But if I look at 100 people at a time, each one is more representative, so I don't see a lot of variety. So I need to do them separately first. Because depending on the sample size, the variation is different. The variance is different. So initially I do them separately. I'm going to combine them eventually. For now I'm doing them separately, taking the population of individuals that I'm assuming is the same throughout, my pooled variance, dividing it by the sample size for the first one, sample size for the second, same as always. Okay? Not that many steps left. Yes.
I get confused by the concept of distribution of means. Because I thought that we were looking at their scores, like different people's
I am, but as soon as I have a sample of more than one,
Yeah.
I'm looking at the sample average score. Now I want to decide, is that a common number to get? Is
Yeah.
that an extreme number, a rare number? So I need to see how the sample average
Yeah.
compares to all possible sample averages that I could possibly have gotten with that number of people. Say 5. I can't look at, sorry. I can't look at the sample average and compare that to individuals. I have to look at how that compares to what I could possibly have gotten. Is it common? Is it not? So I want to see the likelihood of getting a sample like that. So I need to put it in the context of what are the probabilities of getting different kinds of sample averages. And the probability is the distribution of that.
But why is it saying each population's distribution of means? Like it seems like it's saying that.
I have 2 independent populations, right?
But it seems like, unless I'm just not understanding, it seems like they're saying each population has more than one mean.
No. It just means because I have 2 populations.
Oh, okay.
Each one has a mean
Okay.
and a variance.
Okay.
Yes. Yes. Yeah, no, the phrasing I see. Just the. I guess what would be simpler is to say the distributions of the mean. Maybe that's simpler.
Distributions of the means of each.
I think that's worse, but all right.
Throw in more words
Yes.
eventually.
Okay, so I create 2 distributions of the mean, 1 for each population. Okay, now I'm going to just visualize this first. Okay, so I've done it separately, distributions of the mean for each one, because their sample size is different. I need to do them separately first. And now I want to combine them so that I can start thinking of my test. My test is going to use a t-test, which is a single distribution. So when I combine these, now under the null hypothesis, they're assuming the mean is the same. So it's only the variance that's the problem. The mean of this is going to be 0, because I'm assuming under the null hypothesis those 2 means are the same. But the variance, how does the variance, so this guy has the same mean as this guy, because that's what the null hypothesis, I'm working under the null hypothesis and seeing how extreme my samples are in that setting. Should I reject the null hypothesis? So under the null hypothesis, I almost put blue again. Under the null hypothesis, let's say it like this. Under page 0, my mean for 1 is, my population mean is the same as population mean of 2. And I now have the estimates for estimating the variance of each as, what do we call them? SM, what do we call them? I just want to be consistent here. SM1, SM2. SM1 squared, doesn't matter. SM2, variance, standard deviation, doesn't matter. So when I now combine them into a single distribution of differences, with some math here, let's do it like this. Insert math here. You can show that the, what do I call it? I want to call it the combined distribution, but I just want to be consistent with how they refer to it. The difference. Let's call it mu difference is mu, no, it doesn't matter which one, 2 minus mu1, 1 minus mu2, doesn't matter. Because they're the same, they're going to be 0. So the distribution of the differences between the means is 0, because they're assumed to be the same under the null hypothesis. You can show that if you're combining two variables like this, then the variance of the difference is actually the sum of the two. Which, when you think about this, it might make sense. This is a measure of variability. If I'm now subtracting two things, what is the worst kind of variability that I could get? The worst case, as these two things vary in between each other, is the worst variability in each one to sort of amplify to give me the sum of the two. But there's some math here, and you can prove that this is how variance is combined. So, I said we're avoiding some technicalities because it's hard enough already. So I'm taking the two distributions of the mean for each of my populations, merging them into one by way of a difference so that I can apply the t-test. And the variance of that comparison distribution is going to have, the variance is going to be the sum of the two individual variances, and the mean is going to be 0 because under the null hypothesis, excuse me, they are the same. It's only the variance that's the issue. No variance. Okay, so now let's continue. My last little bit. It's actually not that bad. I've seen worse. So the variance and standard deviation, therefore, of the distribution of the differences of the means is going to just be adding the two together, and I get in this example a 1.55. And therefore the standard deviation is just the square root of that, 1.24. That's going to be it. That's it. Everything else is the same. Okay? Just breathe, deep breaths. Everything else is the same. It's only how do I get an estimation for the variance when I have two independent groups, but my t-test requires a single distribution. I need to put them together in a sensible way, which is this way. Let me zoom out a touch, or can I put both? Yeah, I can. So, I've had my research and null hypothesis. I've now done the calculations for my comparison distribution. Population variance, comparison distribution has mean, I don't need to write M there, write a mu. 0, and the difference 1.24, and it has a t-distribution of 7 degrees of freedom, 4 plus 3. Now I'm back to familiar territory, which should be Good. A little bit of a relief. I think we use black. Where's the recording? So I'm looking at my distribution of means. I'm not happy with the m there. I think it could be a mu m or mu, I guess, difference is more appropriate. But this is the distribution, let's say, distribution of differences of means. So let's call it mu difference. That's 0, and the variance, so just be careful here. I've added the variances, and then I take the square root of that. I don't add the standard deviations. It's variance that gets used in the calculations, and at the very end, I take the square root. So whatever you write here, I have my standard deviation of the differences as 1.24. Now I have my degrees of freedom, t distribution, everything's good from now on. 7, and I'm going to decide on a 0.05 alpha. I'm looking at my research hypothesis that was, I suspect that under quiet conditions people perform better, so that the rating, the mean, is going to be strictly greater than in the noisy population. So I have a one-tailed test, and my cutoff is going to be somewhere over here, giving me my 5% on the right. So that I can use the table. I'm looking at a one-tailed test, 5%, 7 degrees of freedom. I get a 1.895, which agrees with the slides. 1.895. Now I'm going to look at my t-score, my observed t-score, which is the difference between the two means. Quiet minus noisy, divided by the standard deviation, or the estimate of the standard deviation, and I get a 3.23, and that's its way out here. 3.23. So I can reject the null hypothesis. I have strong enough evidence to reject the null hypothesis and support the research hypothesis that people perform better in the quiet environment. So focus on the similarities, and there's really only one difference between what we've seen before and this, and it's only in estimating the variance or standard deviation for my comparison distribution. Because my situation is a little different, more complicated, you might say. How I go about getting a reasonable estimate for my standard deviation for the comparison distribution is a little more complicated. But I think we can handle it. We have to. Probably. All right. So think of the diagram. Think of the diagram. That might help a little bit. Any questions before the next example? Just one more example. I'll have to zoom out just a touch. Just too big to fit if I zoom in another step. All right, one more example just to solidify it a little bit. So in this case, I'm looking at individuals who couldn't hold a job and participate in some sort of special job skills program versus individuals like that, but just have an ordinary job skills program. I'm trying to investigate if my special job skills program has a significant effect when I rate the individuals. And I'm trying to see if there is a difference between the two. Maybe I'm not sure if I want to look at a strictly greater than research hypothesis. So just to see some variety, I'll look at it just to see if it's different, better or worse. And the null hypothesis is that it's the same. There's no change. Because my evidence suggests that the sample from the first population is significantly different from population 2 or not enough. So now I have to go and think of this again. Think of this. I have my population, so I need to estimate everything for the population first. Pooled variance. And then I'll go to the distributions of the mean. Then I'll merge the two with a difference. So then maybe 3 steps, I suppose. So let's go to my calculation. I'll try and zoom in here a little bit. So it looks like a lot, but it's not. I have to say that. Because in truth, it's not that bad. It just looks a little overwhelming in the beginning. If you think back, I get so emotional when I talk about this. So beautiful. If you think back at the first time we worked with hypothesis testing or the Z-scores, how that felt and how it feels now. It feels much better now already. It's only been like a week. So you adapt fairly quickly.
I think it felt better before. Personally.
What's your distribution of needs are?
Some perspective. You see something more complicated, suddenly the other stuff's so easy now. That's usually how it goes. And then by next week, this is going to be very easy. All right. So I have 2 samples. I have those receiving the special program, and they score according to some scoring system. And then those that just have an ordinary job training program. Different sample size, independent, different people. So I want to see, is there a significant enough difference between the 2 sample means? So I get my sample mean for the first one, add them up, divide by how many there are, 6. I do my sum of the squares, divide by 1 less, so I get a variance for sample 1, and then I do the same for sample 2. My degrees of freedom is 1 less than the sample size in each case. I have 6 and 8, so it's 5 and 7. Zoom in a little more, I suppose. We don't need these anymore. Deep breaths, that's good. I like that. The key is to not look down. Look up. Don't look down. Don't look down. If I could cover it, I would, but I suppose, no, I'm not
You could like put something.
a little piece of paper and slide it down. Just don't look. Okay, so degrees of freedom in total is then 5 plus 7. So I want to see how we're doing the same thing we've done before and what the steps are. Getting the basics for each sample. Now I'm trying to get the population variance that I'll call the pooled variance. Because my assumption is that regardless of the groups, the variance is the same. Maybe not the mean, but the variance. Under the null hypothesis, the means are the same as well. The pooled variance is now a weighted average of the 2 individual sample variances according to the degrees of freedom. So the first sample is a little smaller, it only contributes 5 out of 12 degrees of freedom, and the second one contributes 7 out of 12. So the second one has a little more say in in what the variance of the population actually is, so I'm giving it a little more say. And I get the pooled variance, which is an estimate of the population variance at 4.16. Everyone with me so far? Sort of. That's good enough. I'll take it. Now, let's visualize again. I like visualization. Helps a lot. Without it, you get lost. You don't know where you're going. So get some sort of picture, some sort of map. So I've done this first bit now. Now I go to how are the means distributed for each one. Because I have samples of sizes larger than 1, I need to see how those samples fit in the distribution. The first one was a sample of size 6. How does that sample mean sit in terms of likelihood of getting something like that? How does it compare with all possible sample means from samples of size 6 from this population? And the second one was a sample of size 8. How does the sample mean that I get there compare to all possible sample means that I could get from a sample of size 8? Move back here, where is it? Up here. Whoops, what did I just do? There it is. Okay, so that puts me over here. So I'm taking the population variance and dividing by the sample size for the first one, sample size for the second one, to get the two variances for the distributions of the mean in both of those. They're two separate ones. Then when I pull them together, let's go visualize again. You'd think I'd put the slides one next to the other so I can just click once, but no, not that smart. So I now have these two. When I combine them for my comparison distribution to use the t-test, I'm looking at the differences between them. I don't have it anymore. Difference between the two means. Well, the null hypothesis said they're the same, so the mean here is 0. And the variance for the comparison distribution of differences is the sum of the two variances. So I have these two individual ones, the variance of the difference, I add them together. I know it's hard to understand this because we're skipping all the math, but you can prove that the variance of the sum of, or difference of two variables is the sum of the variances. I add them up, and then you get a 1.21. So for my comparison distribution, let's sort of recycle this one. I'm not sure which alpha we'll use, so I'll recycle that as well. So let me continue this. So that's always going to be 0 for this kind of test. Now I get variance of 1.21. Take the square root of that to get the standard deviation of 1.10.
What's that 0 number?
Where?
On the top left. What
That is the mean,
mean difference?
because the null hypothesis says they're the same. So difference is 0. So that's always going to be the same. It's only the variance is standard deviation, that's the issue. The mean's not the issue. Because the null hypothesis tells me everything I need to assume. So then I have t distribution, degrees of freedom, 6 minus 1, 8 minus 1, so 12. And I want a 5% again. So let's just go back to the hypothesis testing steps and see how it's structured. So where am I now? I've done all the hard work in number 2. Now I've decided on an alpha. It's a two-tailed test. Even though this tail looks a little longer than the other one, whatever. As long as you get the positioning right. So this will be 2.5%, even though I don't need that for my table. The table takes care of all that for me, just to visualize. Two-tailed test, split into 2. degrees of freedom is 12. The t that I need, I can look it up. Let's just verify if they're doing it right, since we have seen a few typos. Two-tailed test, 5%, degree of freedom, 12, 2.179. Okay, good. So plus or minus 2.179. This would be a plus. And this would be a minus. Since I don't know if my special job skills programs can be better or worse, potentially. I want to play it safe, I don't know which one, two-tailed test. So then I look at my sample score. Well, I take the difference between the two sample means divided by the standard deviation of my comparison distribution, and I get 2.73. Okay, it's extreme enough, not by too much, but it's enough, 2.73. So I can reject the null hypothesis. I have evidence that supports the research hypothesis that the two means are different at a significance level of 5%. A lot of things have been said. I'm not gonna lie, I totally understand how it must feel. But I also know that it's something that you can overcome with not too much difficulty. It's only that beginning it seems a little overwhelming. But put things in perspective, it's only because you're hearing it for the first time. Focus on the similarities. There's a lot of similarities, and only one real distinction. So, just to summarize, I'm not going to read the whole thing. We've gone through the steps. The only issue is in finding the standard deviation of the comparison distribution. So you can see it as, they have it as 5 steps. You can think of the steps however you want. However, you need to look at this weighted average, individual, the weighted average for the population estimate, then the individual ones, combine them, square root for the actual standard deviation. Everything else is the same. Everything else is the same. Any questions on this? By way of examples, it'll get easier with time. We're doing okay. All right. Now there is another example that we can do a little bit faster. The repetition will help me remember. I'll do it a little bit faster, just to get the process, get used to the process, and then focus on the little detail. So in this one, students were surveyed, 2 groups, those that are firstborn and later-born students, to ask the question, do you tend to fall in love hard? These were the samples, 42 and 57, were surveyed and rated a little bit differently. Just one couple. In a very similar way, let me just quickly check what. So we do the hypothesis test procedure first and then fill in the detail, especially here in step 2. So I have my population 1, the firstborn students, population 2, the later-born ones, and I want to see if there's a difference in the average rating to this question. So I just want to see if there's a difference. I don't know which side it's going to be, so again, I have a 2-tailed test. And then our calculations will come in here. So let's go, and I don't have a visualization this time. So I have my samples, and to make it simpler, it's sort of summarized here as the sample size, the sample mean, and the variance is given for me. So I have my degrees of freedom. I'm just going to focus on the steps, not the detail. We've done it a couple of times now. I'm looking at a weighted average to get the population variance. Then I look at the separate distributions of the mean, combine them for my comparison distribution, and take the square root for the standard deviation of this. So let's visualize it here, since it's not on the slide. Then we know the alpha, degrees of freedom will change, and this will change. See the similarity? Very similar. It's only the estimation of the standard deviation that's different. So in this case, I get 0.39. Degrees of freedom is 97. And let's go to my hypothesis test, where I'm deciding on 5% again. And I have a two-tailed test, so I look up the t-score cutoff value. I have 97 in my list. Let's verify that 1.986, they say. So I look at two-tailed, 5%, 97 is not there. What do? They choose the 95, which I suppose is the closer one. 986. 986. Negative 1.986. And then I see what is my t-score observed between the two sample means using my estimate for the standard deviation. And I get a negative 1.85. Oh, that's over here. I'll exaggerate it a little bit. Negative 1.85. So what do I conclude? Or what do I say at the end? Inconclusive. It's not bad, but it's not past my cutoff. It's not strong enough evidence to say that at this significance level, the differences are, or the means are different. Could just have been a little random sample that gives me this. All right. I'll quickly do the rest, but this is essentially it. When it comes to effect size and power, again, because I'm using the t-distribution, I don't have all the tables and all the information at my disposal to do the calculation, but we've done the calculation. In the basic case, we don't need to do it every time by hand. I have these tables to help me get an estimate of the power of the study, and therefore the probability of making a type 2 error. Now, the slight little issue is that this table assumes that the sample sizes are the same, and if it's not the same, then the power is I have to adjust the calculation a little bit. It turns out that, let's just do the effect size first, before I forget. The effect size is what you might suspect. Effect size, D. So it'll be the difference between the two means divided by the standard deviation of the population. Population, not the distribution of means. Population, which is the pool. So just be aware of that little catch. It's always the same. It's always the population. Even though my comparison distribution uses the population uses the distribution of the mean. The effect size does not. So I have different effect size sort of categories there in my table, just to keep my table simple, they don't show too much. And if the sample sizes are not the same, then I have to be careful in terms of which one I use here to estimate the power. For unequal n's, the effective n for computing the power is closer to the lower one. Not exactly the lower one. And it turns out, with a little bit of math, that you combine the two sample sizes by way of this formula that we call the harmonic mean. So this harmonic mean is going to be the n value that you use in your table when the two sample sizes are not the same. You plug in the two sample sizes, you get a value, and then you go back to your table, and that is the n value that you use.